seminar series hosted by the Center for Networked Intelligence at DECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Professor Wouter, and he will be speaking on constrained best arm identification. Koolen is a senior researcher with the machine learning group at the Centrum Wiskunde and Informatica in Netherlands. He is also a professor of mathematical machine learning in the statistics group at the University of Twente. Koolen earned his PhD in computer science from the University of Amsterdam, cum laude in 2011. He was a postdoc at Royal Holloway and QUT Brisbane. He currently works on the topics in machine learning theory and related areas, including game theory, information theory, statistics, and optimization. His interests include pure exploration in multi-armed bandit models, game tree search, and provably accelerated learning in statistical and individual sequence settings, and learning faster from easier data. Over to you, Professor.
Thank you. So welcome, everyone. Oh. Is it working, the mic? Yes, great. So very nice for all of you to come. So I want to talk about constrained best arm identification. So I'll tell you what that is and what we did on that topic. So this is our submission for NeurIPS. So you are the very first audience to see the material. All right, let's click so that it works. So first of all, I should thank the people who did this work with me, who are Tyron Lardy, who was my PhD student. He graduated last week. And Cristina Casimiro, who works at Booking, the hotel company. All right, let's get started. So here is the motivating question for today. So we are, let's say, a company. We're operating maybe some service on a website, and that's the red one. So that's our current version. But we have a smart team of designers, programmers, and all that, and they have created some new versions, and they are constantly sending us emails like, you have to put my version on because it's so much better, right? So you think, well, maybe they're right, but maybe we should sort of try and test this out, this question, which of them is better, before we actually just transition. All right, so how does that work? Oh, maybe first, how does that called? So people, when they talk about trying these type of things on actual subjects, they call it A/B testing, adaptive clinical trials, or sometimes best arm identification. So I will mostly use that last phrasing from the bandit literature. Okay, so how does that work in practice? You have your website, the red one, and you want all your customers to be served with the good current version that you know works to reasonably well. So of all the people that come to your website, maybe it's new customers, maybe it's repeated customers, but you keep on sending most of them to your current website, right? And then as a result, they interact with it and maybe they buy a product. Not all of them do, but some hopefully large fraction of them do, right? But behind the scenes and without anybody knowing or consenting or whatever, you take a small portion of the users and instead you present them one of the new versions, right? Why are you doing that? You want to learn whether these versions are actually, how good they are, or whether they are better than your current one, right? So you show these unsuspecting users, for example, the green version, and also record their interactions of those users with that version, right? And you have these two other versions, so you sometimes show this one, you sometimes show this one, right? And the job of the testing system is to organize that bottom part in a smart way, which means that it can choose which version you present to the next user coming in. And you want to organize this in such a way that you can make the decision as quickly as possible, let's say, which of these is the best, or maybe which of these four. You typically want to include your current version. If it is the best, you don't want to switch. If any of these is better, you want to switch. All right, so this is almost all tech companies that operate websites are running a version of this behind the scenes, sometimes very sophisticated, sometimes very basic, but it is too difficult to base the new versions just on good design. You have to test it. Sometimes things you think are great don't really work, and vice versa. Okay, so we want to consider, yes?
The fact that you have an existing, does that actually change the problem fundamentally, or is it the same if you had 4 systems and you are asked to choose which is the best?
It's actually a little bit subtle. So one thing you could do is you could ignore that you have been running this version for a long time and just throw it in as if you had 4 versions. This would, you would do that if you were running a test from scratch. But if you need to keep your current version in operation, you have to send almost all the users there. And then it becomes very imbalanced. If you take that to the limit, that you actually know how good this is, because almost everybody went there. And it is as if you're comparing this to a known baseline number, right? But if this is like not idealized infinite, then maybe there is you are learning as you go over here as well. Maybe you want to send 99.5% here. That's okay, right? So, but these are sort of small details. You can squeeze epsilon performance or keep things simple by doing those or not. Yeah, but it will not be the topic of where I'm going. Yeah. Okay, instead what I want to do is I want to say, this is not the problem we actually care about, and change the problem a little bit. Okay, so that's this is weird, because there is more slides here than here. How does that work? Okay, I think I just misunderstood my preview. Okay, good. So this is still about the testing problem I was outlining here, right? So I just wanted to show you some earlier works that have nice theoretical guarantees, namely efficient algorithms with asymptotic optimality. So we will see what that means. What's the difference between the different lines? It is the assumptions you make about the rewards that you're seeing. The earlier works tried to make things simple, for example, Gaussians, and I know the variance. It's not covariance. Later work said, oh, maybe it is still Gaussians, but I do not know the covariance. I need to learn that. That complicates things a little bit. And other nice work says, well, maybe it's not such a nice parametric family. Maybe there is some non-parametric. Then you need to do something else, for example, have bounded rewards. And then in all these cases, you can develop algorithms for running that testing system. Okay, so now let's change the problem around to make it more practical. So what do I want to do? So the observation is that classical problem, it's about finding the best arm, which is typically the highest reward. And for that purpose, you model an arm as a random source of scalars. Okay, but whenever you are ordered to do a test, there is very often a background constraint that you have to satisfy. For example, let's do number 3. Yes, I would like my treatment to work, but it has to also be safe, let's say, and not kill you unrelated to the disease, but by causing maybe some side effects or something, right? Or, for example, if you're bidding on ads, you would like to get as many people to respond, but these ads also are expensive. So you pay, right? So you get views, but you pay money. Maybe you have some budget for how much money you are willing to pay to the overall system. Okay, so in And maybe the last one, suppose you're, for example, Netflix, right? You stream videos to users, but the users are having all sorts of devices like smart TVs, mobile phones, maybe they have some gaming computer, and all of these have, in principle, compatible viewers or apps available to them. But it will actually happen that if you push a new version, some percentage of them will just crash, right? And that shouldn't be too many. Maybe it's unavoidable to some degree, but if it's too many, you get bad news, right? So you can see that happen because people they stop streaming in the middle of stuff with no other explanation, like you don't see them back on the home screen. They just vanish. Okay, so maybe there is some toleration for that, but it's typically maybe in the 1 in 10,000 or something. But in the end, that's a constraint. If you crash too often, then it doesn't matter if the rest of the world keeps subscribed for double as long. You would not like that. Okay, so if we want to talk about these constraints, it means we are actually observing two objectives. So the reward will stay, but we will also now have a second scalar basically associated to every choice, which we will think of as a cost, right? And then to model what's going on behind every one of the versions, we now need a distribution on the reward and the cost together, right? So we're suddenly escalating things to these joint distributions. Okay, so let's review that a bit more. So we have now, yes.
Ask 9 questions, but why can't you do the cost, the reward itself? Like if the code crashes, then the reward is a big negative number or something.
Sometimes you can do that. And then maybe you are not in this world, but often the reward and the cost are in completely different units. Like reward could be, for example, views, but cost could be money, right? Or, yeah, with treatment and safety, I think you can have side effects that are bad, but they're maybe not measured in number of years gained, but they're just uncomfortable or something, right? So yeah, sometimes it is one unit, then maybe you should merge it, but I would claim often it's actually incomparable. Yeah. I think the motivation, so I already mentioned Christina worked at Booking, so I think she was thinking about doing promotions. Promotions make more people respond to your offers and buy things. But in the end, I think they care much more about people sort of, they do it for the advertising and the, what is it, the exposure that it gives, more than the extra revenue that it brings. So they see these promotions mostly as a cost, and they have some budget available for this, right? And this could be maybe a borderline case where you could maybe long-term, maybe the revenue is not in the current purchase, but it comes from returning customers. Maybe if you take a higher level picture, it would be a very large delayed reward. That's also complicated. Yeah. All right. Yeah, so I will keep them separate vehemently to keep the talk on the rails. Okay, so what do we want to do? We have these bivariate arms now. They have a reward and a cost scalar jointly distributed. What do we want to do? We want to locate the arm of highest expected reward, but only among all the arms that have their expected cost below some given threshold. All right, so that's our job now. Okay, what makes this interesting? So that there are some earlier works, but they modeled reward and cost as independent. But that is typically not true. If you increase the dose, the drug becomes more effective and also more toxic. So these things often go together. right? I think the cases where they don't are maybe the strange ones. So that means that there is this dependency structure behind the scenes between rewards and cost that is important to take into account. Maybe it's also sometimes helpful, but you have to think about it. Yeah, your algorithm has to reason about it. So what we will see is how that should be done. Okay, and then if these joints are so important, it matters what sort of assumptions we are going to make about them, right? So I'll be trying to be very explicit when I say, you know, the joint comes from this set. Yeah, and okay, good. So just to practice a little bit, here what I've done, if I've drawn the cost axis down here, the reward axis down here. So a distribution, a single arm, would be some probability mass function that lives on the plane. Right? It's always hard to draw, but if you do Gaussians, you can maybe do a covariance ellipse. So I did that. So these are my 5 arms, right? And I put a little dot at their mean. So this is, for example, the green one, arm 3, has average cost 0.75 and average reward 0.8. Right? So in this picture, it is the case that higher reward comes with higher cost. At some point, and I guess that's for blue, you're above the threshold, which is this gamma number. So even though it has the highest reward, the blue arm is illegal. So the constrained best arm is red. Right? So yes. I have trouble hearing you. Maybe we can give a mic or yes. Yeah, so I'm trying to keep reward and cost on a different scale. So, for example, reward could be in this medical setting, it could be, for example, how many years you live extra because the drug really helped you. But cost could be how uncomfortable you feel, which is not related to your lifespan, but it is bad if it gets too annoying, or right. That could be sort of one example. Or yeah. Okay, so this is now the picture. We're trying to learn where basically that red is the best. Okay, so let's try to set things up a little bit more formally so that we can sort of dive into what's the interesting hard bits and technology to solve this problem. So let's start modeling a little. So because I'm going to be explicit about what I assume about my arms, which are these distributions, I will for a while not even commit to it, but just write big M. So big M is what every single arm can be doing. And for me, that's always a distribution on R squared, cost and rewards. And later on, we'll fill in 3 different versions. Okay. If you have one such arm, it will have a mean. That's 2 numbers, which I will write M1 of the arm nu and M2 of the arm nu. So that's reward and cost. And then we think of the overall learning problem is it has several arms, and we're trying to learn the constrained best one among them. So for us, a bandit, which is this learning environment with k arms, is a choice of k arms from M. Okay, so if we have all that, we can talk about what is the constrained best arm, and it is hopefully what we already discussed. So we take some threshold in mind, and then we look over all the arms. We only keep an arm if its cost, if its average cost is below gamma, and among those we try to maximize the reward. All right, so this arg max is what we're looking for. All right, so now there are some interesting complications. The first one is, what happens if all your arms are worse than gamma? That can happen, but that is interesting to us. We want to know that, right? So we want the learner, the whole system, to be able to tell us, hey, you asked me for the constraint best arm. Sorry, there is no feasible arm. So we introduce an extra special answer, none, for that scenario. Okay. The other thing that can happen is that the argmax is actually not uniquely defined, but there are several guys that turn out to all be the best. This setting we can actually not handle. It would be an infinitely difficult learning problem to figure out which is better among two equal things. So we're just gonna assume that away. Right? It's a very classic move in the bandit literature, but we will assume that we are never going to get presented with a bandit in which two things are equally hard. All right, this sounds like a cheat that I'm doing, but I think I'm okay doing it because there is always sort of the more complicated version where you do take this into account with maybe I want an epsilon best arm, and then it's okay if two things are equally good, and it will not create an infinite complexity. But I will not go there in this talk. Right? So for me, I will stay on this level of no ties. So whenever I say for any bandit, there's a little asterisk that says no ties. Okay. Good. So then what have we got? So this mapping, the best answer map, takes in a bandit and spits out an answer. And it's a little bit funny, but there are k plus 1 possible answers and only k arms. And another thing to observe about it is that I put into this map the entire bandit, which was a vector of distributions. But in here, the only thing that matters about these distributions is actually their means. Right? So it sounds scary, but it will operate always through the means. So that will help us a lot further down. All right, so let's practice a little bit more. By the way, these are also the instances that I will run all my experiments on, so I'm already warming you up to like them. But let's do a few more constraint best arms. Right, so in this world, yes?
I take the variance of, suppose it was a univariate arm.
Yes.
And I take M2 of B to be the variance of arm B.
Yes.
Then this could be asking a question like, I don't want an arm which is giving me a very, answer, a reward with a lot of variance.
Yes.
And so I constrain the variance of the arms, and among the arms that have less variance, give me the best arm.
Yes.
Is that also a special case of the kind of questions you're asking here, or is that something outside of the
No,
purview?
it is a special case. So, okay, almost. So if you had said second moment, then I think it fits perfectly. If you would have your cost be the reward squared, right? It would be completely dependent. So this would work in a model for the arms where that dependence is ideally either one of the legal options or the only way to do it, right? If you do variance, then to calculate that, you need to mix the square and the not square. So I think then you will slightly fall outside. Yeah, but it's very close to, yeah. Otherwise, you would have to go like nonlinear functions. So, yeah, but it won't fit perfectly. Yeah. It's a nice problem, though, I guess. So I think the technology in here might help. Okay, good. So we were looking at some best arm setups, right? So over here, these two arms are infeasible. These are okay, but not very good, and blue is the best, right? We want to learn blue. Here, I think everybody is feasible, and blue is the best, right? Over here, everybody is infeasible. So here, the answer you should give is none. right? That's what you want to hear. All right. So now about these models. So what am I going to assume? And we'll be doing 3 versions, right? These are somehow very representative, but definitely not everything. So the first one is maybe for simplicity, namely, so all these models are describing distributions on 2 numbers, right? So you can do two bivariate Gaussian with a fixed covariance matrix, maybe identity, maybe something else, but you fix it and all the arms have the same. All right, in that case, your arm model would be, you can still vary the mean, but the covariance is fixed. Okay. A second, more practical and also larger model is where you don't fix the covariance. So then your model for every arm is that it's normal, but with some mean and some covariance matrix. Okay. And the last one is we're going to do the upgrade of that non-parametric unit interval. So we're going to do every distribution on the unit square. So we have bounded mean and bounded cost, bounded reward. So that would be all the distributions on 0, 1 square. Right, so those will be the 3 cases that I will instantiate all the results to. The first 2 will hopefully give nice expressions, and maybe the last one is the one where you can actually have some true belief that your setting is actually in the model. Right, nothing is really Gaussian. So these 2 are for theorists. Okay, so let's go over that whole testing interaction then. So we'll work in what is called fixed confidence. And that means that the algorithm will be given a parameter delta, which is the proportion of mistakes that it is allowed to make. Okay, so what we're going to do is we're fixing a bandit instance. And then we will allow the learner to perform tests in rounds. What does it mean to do a test? The learner will pick one arm by choosing IT, one of the arms, and the learner will receive a reward cost pair. So 1 reward, 1 cost, drawn from the arm that the learner picked. Okay, so that will go on for as long as the learner likes. So that's why there is this end time tau here. That's also under the learner's control. All the orange things are under the learner control. And then when the learner decides that it's time, it has seen enough, it stops the loop here. And at the very last thing it does is it will output what it thinks is the correct answer for the bandit that it's running in. So it's one of these arms or none. Right? This is the job of the algorithm. Right? And then to fill in all the details, what we need to do is we need to pick all the orange bits. So we, as the designer of the algorithm, have to figure out a smart sampling rule, stopping rule, and recommendation rule. No, so
when you start learning, then you pick
over that. But the thing I want to, the world I want to operate in is the stopping time itself is a choice that is adaptively made by the algorithm. So in that sense, it's like a stopping time in the sense of probability theorist lingo, right? But maybe it's easier to think of this as the algorithm at every iteration can decide, do we stop here or not, right? And yeah, so the runs will have different lengths. Right, the other setting that you were referring to, what if we put a fixed number here? Then you typically flip things around and you optimize the probability of error. So I'm going to do the other one where I fix the probability of error and optimize the length. So I think that's on the next slide, yes. So here are then the rules for algorithms. Namely, I'm giving it this confidence parameter. And what I constrain the algorithm to do is the probability that it makes a mistake should be at most delta. What does that mean? For every bandit that I run my algorithm in, the probability that it at some point decides to stop and it gives me the wrong recommendation, that is this small tuned probability that I control. Right? Algorithms that have that are called delta correct. So they don't make too many mistakes. Right? But I guess one way to be very sure is to just take many, many, many samples. Right? So among the delta correct ones, not everything is equally desirable. The good algorithms take few samples. So we're going to score an algorithm by its sample complexity, which is the average time it takes to stop. Right? That, I think, it still depends on the bandit you run it in. There may be easy and hard bandits. So this is actually a multi-objective criterion right now that we have to minimize. But it turns out we can minimize it somehow for all bandits at the same time. So we don't have to worry about trade-offs and all that. Okay, so let me now sketch you how we're going to approach this problem. Part of that is sort of a path that has been run many, many times. There's like, I think dozens, maybe multiple dozens papers that are doing the same steps we are doing. And then I will zoom into what's different because we went constrained. Okay, so what is this well-trodden path? It's pioneered by Garivier and Kaufman in 2016, and they called it track and stop. They first, and that's, we will also start there, they show that any delta correct algorithm will need a certain number of samples. So this is an information theoretic lower bound on the sample complexity. And then they stare at it and they say, this lower bound is very good. It has actually two properties, namely, it's not only a lower bound, but you can match it. And the lower bound, in the way it is written, actually reveals how you should match it. So it actually gives you for free an algorithm to have that good of a lower bound. Okay, so they get out of that lower bound a way to figure out how many samples to put in each arm to actually get that lower bound, but as an upper bound. An algorithm is sort of distilled from that. And that allows to design the sampling rule. Then you still need a stopping and a recommendation rule. So they do some likelihood ratio test to fill that part of the algorithm in. And that gives them the delta correctness. And that is actually generic. We will do that too. And combining all these things, they will get their asymptotically optimal algorithm. Okay, so what do we need to change? Because we have constrained best arm. And it's actually the very starting point. So we need to update our lower bound. Okay. And everything downstream will sort of stay the same, but with the modifications percolating. So for example, we get different optimal sampling proportions falling out, which we will then sort of try to mimic in the same way as they did. Right? So we want to see, okay, what are these new sampling proportions and how do we calculate them for our constraint problem? Okay, so about that lower bound. So this is the part where it hurts a little bit. What I will be doing is I will try to talk about some of these things as just blobs with an identity that will come back, and then at some point you become friends with it, even without looking inside. But let me try to go over it. So what Garivier and Kaufman show is that in this delta correct fixed confidence world, if you are a learning strategy that is running in some bandit new, the number of samples that you need before you stop is bounded below by two parts. But the second part is always very easy. It will just measure the strength of how many mistakes you allow. So it is written as a KL, but this is actually something that just scales with delta getting tighter when it goes to 0. So this is the contribution from you wanting reliable answers. And the second part is for us the interesting part, which is a quantity that depends just on the bandit. So it's doesn't have any delta in it. And this quantity, actually it's reciprocal, but all right, is defined by a two-player min-max problem, where there is an outer player trying to put weights on the arms, and there is an inner player trying to look for other bandits. So this new prime is also a bandit, but these other bandits have to have the property that they disagree on what's the answer. For them, it's a different answer than the one for nu. Okay, once you have found such another bandit, you measure the weighted information distance, so weighted by the weights that we will think of as the proportion of samples that is picked by the learner. And this information distance is the Kullback-Leibler between the arm in the bandit you're at, nu, and the bandit that was chosen by this sort of evil opponent to make the answer different. All right, so if that was a bit of too much, I can understand that. That took me also months to get to this, but we will sort of mostly look at what's down here, because this is the part where the constraint thing changes something, because we changed compared to regular best arm, what's the definition of I star, right? We added that among the arms satisfying the constraint, and that wasn't there before. Everything else is the same as in the original 2016 paper. Okay, so now let's crunch a little bit until an algorithm falls out. That's our goal. Okay, so the first thing is that this minimum search is over other bandits.
You should be different than I star mu prime, because as an adversary, you're trying to like pull the system.
Yes.
But why this the linear combination of KL comes from? This is coming from the information theory lower bound. Is that where it's this?
So that is true, but the way I want to think of this, like some steps down the road, I will also tell you that it's not only a lower bound, it is possible to design an algorithm to actually match this up to some small stuff, right? So in that sense, it is not just, oh, I did an information theory argument.
No, I
It's
understand that, but I'm saying that the original this scale thing comes from the information theory lower bound, right? Is that
this one?
Yeah, that's
yes,
that's
yes.
what. Yeah.
Yeah. Yeah, it's really the very rough story is if you have two bandits and the answer you are supposed to give is different in these two, then, and the only thing that you see is samples from them, then if they're not so different and you haven't seen many samples to inform you about the difference, then you shouldn't be able to answer yes.
It's sort of like the fraction of samples you see for arm that work.
Yes. Yeah. That's right. And what determines that? In principle, the algorithm, the learning algorithm is able to adaptively allocate these samples. So that's something, if a smart algorithm can really try to optimize, that at least you're looking in the places where the differences are. Yeah. Okay. So the way it's going to work is we will crunch and crunch and crunch until we get to a spot where we can go, I know how to calculate, I know how to run. So it's going to be a few steps. So the first step is to say that best arm function, we put in a bandit, but it actually depends only on the means. Okay, but KL depends on everything, not only the means. So, but we can split the search as a search over the new means, so the mean for lambda prime, and then we can sort of delay the search for the rest apart from the mean as far inside as possible. So that once you fix the mean, the search for the rest of the new prime over the KL, let's call that KL_inf, so that we can rewrite this as this max what was there, a min over means, and a weighted sum of KL_infs. Right, so in a way it's equalities, so we're not doing anything, we're just hopefully massaging the notation. And but if you've seen KL_infs style things before, then maybe you are now sort of happy. Sorry?
V prime is equal to lambda, right?
Oh, yes, that's right. This is still that same new prime. Yes. Exactly. So we're now at the max min KL_inf. So let's copy that, max min KL_inf. So now we want to get at least some intuition about what is that KL_inf. But that depends on the model for the arms we assume. So I put some examples here. For example, Gaussian arms. If you're in the fixed covariance world, then KL_inf is just the square difference between the means, right? But if your covariance is not identity, then that also matters, right? So this maybe you have seen. If you go to the unknown covariance model, so that makes the search over new prime richer because it can play with the covariance as well, then you can also calculate that KL_inf. And it turns out you still get the difference between means all squared with the covariance matrix, but then that goes all together in a log 1 plus. Right, so this is in a way something that rolls out of the calculations. All right, so now we have two instances. I didn't write the bounded one because it's not so insightful. But so this is the expression that goes in this spot, right? And hopefully now that max min already becomes more tractable. Everything is in, this is r to the k, r to the twice k. So now we're at least not optimizing over distributions anymore. Okay.
Last line is not.
Oh, yeah, okay, so good point. So KL_inf is a very asymmetric thing in that it's optimizing over the second argument. And for that, I'm fixing the mean, but I let you optimize everything else. But in the first argument, I am still putting the full distribution there, which is also where the sigma comes from. This is the sigma of the thing that sits in the left, right? And so in the lower bounds, that means that your overall expression still depends on exactly in what bandit you are. Its sigma shows up through this in the sample complexity. No, so that depends. But in the fixed covariance model, everybody has the same sigma. So there, yes. In the unknown covariance model, maybe if we go back one slide. So the sample complexity is evaluated at some bandit. Its arms have some sigma, can be different between arms. And in the search inside here, you're again optimizing over the sigma to make it as confusing as possible.
The fixed sigma unknown, but for the mean, for lambda, you've already done the optimization over all possible sigma.
Yeah. Yeah, so the reason the log shows up is actually because of the optimization over the sigma that goes with the lambda. Yeah. All right. So now let's try to tackle the bigger problem. So we saw that KL_inf is either as it's basically a distance norm squared, or maybe with a log 1 wrapped around it, but it is sort of growing if you move further. Okay, so now we need to figure out how you get to have a different answer than nu. So that's what this is supposed to illustrate. So here is my bandit nu. It has 1, 2, 3, 5 arms, 6 arms. And this is the constraint. So everything there is infeasible. So this is the best arm. Okay, so now I want to move to nu means. And I want to end up in a spot where the constraint best arm is different from this guy. So here are a couple of ways to do it. The first one is to make the current best arm infeasible. Just transport him across the feasibility threshold. At that point, he's no longer the constraint best arm because he's infeasible. Okay, what is the cheapest way to bring him across that threshold? And that is that KL_inf that is informing you about how much that costs. And we saw that it depends on the sigma that I did not visually illustrate, but there is a sigma behind this arm. And that means that it is not always the straight path that is the cheapest. If sigma is slanted, this might be the cheapest way to make this arm infeasible. So that's why the arrow is not straight. For independent, it would go straight. But independent is a bit boring and impractical. So this is the common situation. So first way how to satisfy these constraints is make the current arm infeasible. Okay, second way, we can look among the infeasible arms and bring somebody back. There might be really good guys up there, like this guy. And if we transport them to become feasible, maybe they are still already better than this guy. So we don't have to do anything else. We make them feasible. That will move their reward as well because of the sigma effect. But if they just end up above the current best, then they are now the new constraint best arm. Okay, so these things move only one arm. Two more things that can happen. We decide to move this current best arm down and another arm up. And again, we have not orthogonal arrows. So when we move this guy down, it might go there. And we move this guy up, it might sort of go sideways. But if we do that enough, they cross over. So I drew them at the spot where they are actually now just crossed. Right? And now this guy is the best arm. Okay, so that is another way to get you to satisfy this constraint. And the last one is to take an arm that was infeasible, make it feasible, but if we do only that, it would not be better than the best arm yet. So we also drop the best arm. So we move two arms, this guy drops, and this guy goes to the same level and to the border of feasibility. Okay, so it's in all these several dozen papers that I just sketched, that this is sort of, let's say, half of the part of the work, figuring out this constraint here on that minimum. That's always sort of a non-convex thing that splits in several cases, and you have to cover them carefully and ideally get to a bunch of nice subcases and then glue them together. Right? So it also goes like that for us. But in the end, the good news is there are only 4 ways to find a good lambda. It has to do one of these 4 things. Okay, so let's see, because I think, how are we doing on time? 10 minutes. Yeah, so I think it's okay, actually. So the next thing we want to do is, among these 4, we would like to find the one that minimizes this objective, right? Because they're not all equally cheap, and we need to go with the cheapest. Okay, so if we don't know what KL_inf is, can we actually still figure out what the cheapest other configuration of memes is? And as you saw already, well, we just need to move 2 arms, either 1 or 2. Right? So we only have to look over sums of KL_infs that have either 1 term or 2 terms. Okay, so let's introduce some notation for that, which is either it has 2 terms or it has just 1 term. The hard case is the 2-term case. What configurations do we encounter still among the lambdas that we just saw? Well, you're looking for 2 arms that get moved, so they need a new lambda. What do these lambdas have to satisfy? The second guy, I'm calling him J, has to end up better than the first guy. He has to have a higher reward. And the second guy has to end up feasible. All right, so this is now, again, a reduction in complexity because it's only talking about 2 arm combinations. and it's summing these weighted KLs. There was also the whole business about moving just one arm. When we moved only one arm, we always moved it in the second coordinate to the feasibility threshold. So we need also to know how to do that. And we moved it either up or down, that both happened. But somehow we can extract that and give it a name. So what we've done right now is we're crunching the problem without specifying the model. And we figured out that if we have a way to implement those two functions for our model, then we can go with it. Then we can solve all the higher level problem in terms of those guys. Right? What would that look like? So we're back to our min-max problem. So the max is still there. But now, depending a bit on the cases, we have sort of written that whole search over if you move two arms, then you always move the current best, and you're looking for another one to move. And then how expensive is that? Well, that's what C1 tells you. Right? So it's sort of going over all the possibilities and giving them a spot. Right? This is if you move just an arm, namely the best one, across the threshold. That's another way to go. And here you have to move somebody back in that was infeasible. Okay, we're almost there. So this is sort of not for human consumption, unfortunately, but let me just tell you the good news. There is one more thing you can do after you've introduced all the C notations, which is to, in the end, express the overall sample complexity and also the associated weights in terms of mostly C's and some inverses of C's. So I'm writing here WJ star, don't look too much, but WJ star is the third argument that makes a C1 equal to some other thing. So it's an inverse C1 if you want in the third argument. Once you have those, and you know what C1 to, what C tilde to pick, so there is a complicated formula for picking the C tilde. But then the claim is you have solved the entire min-max problem. And you have the value and also the good weights. Okay. This sounds horrible, but it's actually a recipe for solving. So you can figure out this expression has a monotone behavior in C tilde, so you can bisect it to solve this. These guys are all increasing as well, so you can use bisection to invert. And so all of this is like 2 levels nested bisection once you have the C1, C2 available. Okay. So that's written here. So you can, once you have the C1, C2 oracles, you can do the rest with nested bisection. And actually, if you look at the original paper, what you're seeing is we're not actually even paying for going constrained. It is the same thing as regular best arm. Okay, so now we need the C1, C2. Okay, so we have our 3 models. And let's remember what was C1. You input 2 arms, and you're looking for how to make the second one the best and also feasible. And this cost was weighted KL_inf, right? So it was about doing this or that. Okay, so this is the part where, as a programmer, you now are super happy. As a mathematician, you go like, this is so dirty. But it turns out you can have a closed form expression for the C1, and I'm now in the known covariance case. So it's a whole bunch of case distinction that try to figure out which of these pictures is actually the cheapest, and then there is a closed form formula for the cost. Right? And you recognize that sometimes you have to move in only one dimension, so you only see either 2s or 1s, and sometimes you have to move diagonally, and then there is some joint norm thing showing up. Okay, so nice to know, I guess, but the good news is it's basically constant number of operations, right? So this is extremely cheap. So this can be in an algorithm, no problem. Okay, horrible, let's not go into that. Good news, constant number of operations per arm for the for the fixed, unknown covariance, right? And then I highlight some other stuff. It's not a convex problem. So there is multiple possible solution points you need to check by solving actually cubics and doing some careful keeping all the case distinctions apart. But after you've done that once, you have an oracle for that. And finally, the C1 for the bivariate case. So this looks entirely different. And it's because I have one optimization problem left. I need to look over 3 variables that show up in here and there of some weighted combination of expectations of logs. Right? So I'm pretty happy with this, but it's completely different. The good news is, I guess, is that there are not very many variables. So there's 3 variables. The constraint on them is intersection of half spaces, 6 of them. And if you want to use this for calculation, especially in the case where the distributions have finite support, you can do some things. For example, run ellipsoid to optimize over the B's. It's convex in, well, actually concave in B. And you would end up running with order n steps per arm per round. Right? So this is actually getting expensive to some degree, but that's okay. All right, so now let's do some experiments and wrap up. So how do we put all these calculations that I just showed you into an algorithm? Right, but what we have actually built now is a way to compute the characteristic time and the oracle weights in all the 3 cases. So what are the other steps? We need to estimate the bandit. After that, we can plug that into those characteristic time and oracle weight functions and get good weights for that estimate. And then we can rely on the estimates converging to argue that these oracle weights get better and better. If we combine that with likelihood ratio stopping rule and an empirical answer recommendation, then we actually get that the whole combination is asymptotically optimal in the sense that if you take the confidence to 0, so that's more and more strict, and you look at the how the sample complexity scales with delta, you find that the leading factor is again the same T star from the lower bound. Right? So in this sense, you have now matching upper and lower bounds. But actually, there's no innovation in any of this right now. It's just a pull from the shelf recipe. Right? All the innovation was in these calculations. Okay, so let's see if it actually works. So I put those pictures in and calculated some expected number of samples. So there is 4 of them. Let's just pick one. I don't know. Let's do this. This one is called hard because it's it has 5 arms. 1 is infeasible, so you should be saying arm 2. So good. So hard is here. The algorithm that I just described you is called track and stop. So it takes 2,600 samples on average. Okay, what are we comparing that to? That's actually a tricky question. So we had to make up a whole bunch of other algorithms to fight with because there was nothing off the shelf. This one is crazy, so it's also not better. This one is sampling with the oracle proportions. It's weird, but that's always worse. This is uniform sampling, so that's really practical, and it's often done if you don't care about being smart. But in this case, you would have more than twice the samples, right? And then there are some versions of top 2, so they are getting quite close to us. And racing, where you successively try to eliminate arms that you know are not influencing the answer anymore. Also not as good, right? And then this was a weird thing. We ran the vanilla track and stop, ignoring the constraints, and did some post-processing to get rid of the unconstrained best, but it also didn't work as great. sorry. So you calculate on the actual instance the optimal proportions and you sample according to those. Yeah, that always happens, regardless of the problem. And it's one explanation potentially is that in all of this, we are not running with asymptotically small delta. We are running with 1%. So we tolerate 1% errors. So if the asymptotics are not yet kicking in, that could explain this, right? What is surprising is that this doesn't suffer from the same. But I think I calculated here the lower bound that you would get at 1%. So it's around 2,000, right? And this is 2,600. So the actual run, the samples is more than that, right? And so you could say it's somewhat close, but it may be not asymptotic because these things actually get quite close together. So this might actually improve with smaller delta. But it's funny because somehow this algorithm gets an unfair advantage out of its design because this is the smartest proportion. All right, so this is somehow on different runs adapting a little bit to what's happening in that run, and that gives it somehow, it's strange, it's not understood. Like if you talk to any bandit person, they would have done this and they're also confused. Yeah. So these guys are in percentages, how much proportion of the time you should be sampling each arm to get this behavior. So these are these oracle weights. So in this picture, the high two are 2 and 3. So these get 40% of the samples. Around 20% goes to this guy to figure out that he's infeasible, that if he's not, then he's the best, so that's important. But apparently it's harder to discriminate these from each other, maybe because they're so close in reward, so these get higher samples than this. And then there's sort of a super marginal attention on those guys, because you quickly figure out they are not good. They are feasible, but not good. Yeah, and in all the other models, yeah. All right, so we were quite happy about it, in the sense that we actually tried, because I'm selling you this one, but in all these guys, we also had to go through the work of adjusting everything for the constraint case, and in some scenarios that wasn't quite obvious. So there was sort of a research project to help the competition along to then beat them, which was not clear that it was going to happen. Like I didn't put, let's say, black, but I don't think we're everywhere the best all the time. I think there might be somewhere somebody else is slightly better. Yeah, for example, yeah, this is slightly better than this. Yeah. Okay, one more thing, and then we'll stop. So I talked to you about that dependency, right? That's sort of an interesting thing. If the arms are dependent, reward and cost. Yeah, it's important to learn about it. That was my claim. So what I'm doing here is I am making a family of bandits where the only thing that I vary is the coefficient of dependence. So I'm fixing two arms, one at the origin and one somehow it's worse, but what is that? Above the constraint, which is at 2/3. And I am varying the off-diagonal entry of the covariance matrix. I'm calling that rho. The diagonal entries, I keep them at 1, but the off-diagonal, I'm playing with it, and I can vary that from -1 to 1 to stay positive definite. So it's mostly the same bandit instance. What I graph here is the optimal sample complexity. Okay, so that's the blue guy is how many samples you should take per unit confidence. There is no multiplication with the log delta as I change the dependence. So this says the best case scenario for you is full positive dependence. And it gets harder and harder and harder. With full negative dependence is actually the hardest. Okay, so that optimal asymptotic algorithm is actually following that curve, so that's good. And then you could ask, yeah, but how important is it to actually follow that curve? For example, what happens if I just do uniform sampling? So then your sample complexity would be this green thing. So it is actually the right behavior in one point, and otherwise it is always suboptimal, right? And this gap here, I think it's quite suboptimal. And the other thing you can ask is, what if I pretend that rho is 0? I just behave as if they were independent. That would, I guess, work fine if rho is 0. If it's not, you would still stop later. Is it by a lot? Well, somehow it depends, but mostly on this side, it's a big gap, and here, not so much. Right, so each of these other competitors, or not competitors, but maybe simpler things that you could do, have a regime of the settings where they are quite a bit away from the optimal behavior. So there is no sort of a simple thing that works most of the time pretty well. That's the message. Yes. Oh, that's a good one. I think I played with that because I was always also curious. Is it 0 or is it a small number? I think it is actually 1 point something. So it doesn't actually go to a hard 0. I think that would also be surprising because you have full correlation. So I think the reward is a copy of the cost, but you still need to know which of them has the high reward or which of them, I mean, it's a copy. So super high reward is bad. It's not a copy, sorry. The mean is not 0 of this guy, but the offset of the mean is the same in both directions. So I think there is not, the learning problem doesn't evaporate. It's just small. Yeah.
Why is that? Yeah.
Why is it flat? So good question. I guess the algorithm that assumes that they are independent is not actually using the fact that they are very dependent. And so for it, if you ignore any correlation, everything else looks the same, all in this part. Right? The samples from both sides look the same. It's just that they're correlated. So the sampling rule actually does not change based on what's happening here. The stopping rule still does, because we coupled everybody with a delta correct stopping rule. So even if you're thinking that rho is 0, in reality it is not. We cannot use the stopping rule for rho is 0. That would not be delta correct. So we use the correct stopping rule. I don't know in more detail why we should expect it to be flat. I'm struggling because my explanation would probably also make it flat here, but it's not. Okay, we can think about that maybe in the break. All right, yeah. Okay, so let's wrap up. So what we did is we went over the 3 cases that were studied before, and we made these 2-dimensional extension of all of them, where we went with a constraint, right? So the constraint best arm problem, and we looked at how to implement that. Okay, so we motivated why these constraints are there. We talked about bivariate distribution. And then we ended up crunching a whole bunch of computations and simplifications and case distinctions and got these asymptotically optimal algorithms out there, right? And one important, or not, one fun thing that arose sort of in the middle of that was that we want to play with different models, right? But we don't want to redo the whole analysis all the time if we change something in the model. So we extracted these C1, C2 functions. That's part of the problem you can solve in terms of those. And then when you have changed your model, you have to redo just the C1 or C2 oracle, right? And we did it 3 times, but I'm sure there should be more cases where that's interesting. Okay, we managed to implement things efficiently for the 3 models. For the third one, there was a little bit of order n, which is scary, but there are some tricks to get that less bad. And that meant that in all the cases that we tried, we could actually run, you know, thousands of repetitions up to thousands of sample size in right before the NeurIPS deadline. All right. Thanks a lot for your attention. And I'm here the rest of the week, but also right after the talk. So if you want to have more conversations, questions, clarifications, then I'm very happy to talk. Thanks.
Thank you very much, Professor, for an interesting and informative talk. So we will conclude this session with just one question.
So what's the difficulty in going beyond bounded support? Once you encapsulated it into a Koolen formulation, now what's the difficult part there?
I'm not sure there would be any. I think we never tried it. But judging from what happens in the bounded support case, you get to play with all the covariance structure that can exist on 2, let's say, second moment constraint variables. But it would probably look a lot like, okay, sorry. So what happened here was for the bounded case, it is somehow not quite twice the scalar case glued together. Right? It looks a little bit like that, but it's not. So there are, for example, shared multipliers B2 here and here that are sort of making the 2 arms communicate. You don't really see the optimization over the covariance happening anymore, but it is sort of so I would expect that you get sort of a variation of this with maybe some squares of the outcomes happening, right? But you would have maybe R squared, C squared, a cross term, all with multipliers perhaps. I don't know if you need an assumption on the cross term, but so that's unexplored, but I think it's within reach. Yeah.
If you still have more questions, please feel free to interact with the professor while having a cup of tea at the EC Coffee Hut. Thank you all and have a great evening.
Good.